In sac214 number 6, we're asked to solve for the current through this resistor 78.0 seconds after this switch is closed. What we've got here is a parallel combo of two capacitors in series with a resistor and a seed of EMF. So this is a standard RC circuit charging, except that in the place of a single capacitor we've got two capacitors in parallel. Let's start by replacing that parallel combination of two capacitors with a single effective capacitor. I'll call it CP. From your formula sheet, or just what you know, the effective capacitance for capacitors in parallel is just the sum of the two individual capacitances, which will be 20 millifarads plus 25 millifarads in this case, or 45.0 millifarads. Okay, we've got the same resistor, same seed of EMF, but an effective capacitance replacing that parallel combo. Okay, here's the critical part for this problem. At time 0, the charge on this capacitor, so that's the instant the switch is closed. So we have this circuit, but no time has elapsed yet since it's been closed. We've got 0 charge on this capacitor, and that means the potential difference between the terminals of the capacitor is 0. So this conductor down here, that's this whole conductor down here, I'll call it the red conductor, and this conductor up here, the green conductor, are at time 0 at one and the same value of electric potential. There's 0 charge on the capacitor, so Q is equal to CV, V is equal to Q over C, 0 over C is going to be 0, that means 0 volts across here, that means the red and the green conductor are at one and the same potential. And that means that the potential between the terminals of the resistor is the same as the potential between the terminals of the seed of EMF, because the top of the resistor is connected to the top of the seed of EMF directly. The bottom is not. However, this green conductor is at the same potential as the red conductor, which is connected to the bottom of the seed of EMF. So for time 0 only, the voltage across the resistor is just script E. And I can use Ohm's law in the form E is equal to IR for the case I is equal to 0. I sub 0, I is the current at time 0. I sub 0 is the current at time 0. Solving that for I sub 0, if IO is equal to script E over R, which is 28.0 volts, divided by R is 18 kiloohms, or 18 times 10 to the 3 ohms. That evaluates to 1.55555, I'll call 1.556, keeping one extra sig fig, times 10 to the minus 3 amperes, I'll call that milliamperes. There's the times 10 to the minus 3. So that's an intermediate result that's going to come in handy, because in an RC charging circuit, the current through the resistor is given by I is equal to the current at time 0 times E to the minus T over tau, where tau is the RC time constant. So the current through the resistor dies off exponentially. Starts off big at that value and eventually gets to 0 by the time the capacitor is fully charged. Okay. We need tau. This is our formula. We essentially just have to evaluate this at t is equal to 78.0 seconds, but to do that I need tau. I'm going to go ahead and find the value of tau rather than replacing it with the symbols RC, which is what it is. tau is equal to RC, which is the 18.0 kiloohms, kilo being 10 to the 3, I'll write it that way, times C, our effective capacitance is the 45.0 milli, is 10 to the minus 3, times 10 to the minus 3 farads. An ohm farad is a second. This evaluates to 810, so we've got tau is equal to 810 seconds. It's good to 3 sig figs. I'm not going to make it clear to the reader that that's the case because this is just an intermediate result. I'll treat it as having 3 sig figs. So I'll go ahead and plug in for the quantities we've got. I0 1.556 milliamps. Could write that as times 10 to the minus 3, but I see it's just multiplying a pure number, so I'm going to stick with that. Times e to the minus t. They wanted us to evaluate it at 78 seconds after the switch is closed, and lowercase t represents time that's elapsed since the capacitor started charging. So I'll go ahead and substitute the 78.0 seconds in there for t. And tau, we said, was 810 seconds, and that evaluates to 1.41 milliamps, rounded off to 3 sig figs. So this is unitless. E to the negative of this is unitless, and then I'm multiplying that by a certain number of milliamps, so the units work out. So I think I want to specify this is at 78.0 seconds. I, in general, is this expression with I0 and tau now known. Evaluated at 78 seconds, we get 1.4 milliamps.